Okay, hi Guy. Thank you for joining me today. Can you hear me in that side of the room? Yes? Okay, good. My name is Marco Ortisi, and I'm net citizen since 1999, and I'm senior penetration tester and involved in IT security since, 1999. And there is my email address there if you want to get in touch with me. So, what about the topic? In this topic, I will try to explain you how to recover a RSA private key from a TLS session when some preconditions are met. And to do that, we only need the ability to sniff traffic, TLS traffic, or just interacting with the TLS service. And this is done via a side channel attack. Side channel attack, I've taken the description from Wikipedia, which is pretty accurate. So actually, we are not going to attack the encryption algorithm itself, but we are using some extra source of information, just like timing, power consumption, on electromagnetic leaks or any other kind of extra source information to break the algorithm. So this attack has a very deep root in the past. Actually, in 1996, Arjen Lenstra demonstrated that if you calculate a RSA signature, and you do that by using an algorithm called RSA-CRT, and there is some hardware error while the calculation is occurring. Basically, there is the possibility to derive the private key. So before to continue, first of all, what is RSA signature? So I probably know that you are confident with the concept of public key encryption. But basically, in the RSA encryption, if you want that someone send you an encrypted message, you distribute your public key, and this person encrypts the message with your public key, and actually you decrypt the message with your private key. That, as the name suggests, you need to take. You need to basically you don't need to share the private key, of course, because from the name it is private. The signing basically is the opposite operation, the inverse operation. So we use the private key to sign a message, which is actually an encryption operation. And the person that need to check our signature use the public key to decrypt that. So during the 2000-2001, someone conjectured that it was possible to recover a private key from a smart card if the same precondition that Lenstra described in 1996 was met. But basically, to do that, we required physical access to the device. And in 2001, there was a similar attack demonstrated against OpenPGP. So basically, if you had access to the keyring containing the encrypted private key, and you can manipulate, the file, you can modify some parameter, maybe with bit swiping and things like that, and you can get a signature signed with that key, with that modified key. You can basically derive the private key as well. But all this attack basically has been demonstrated if you had local access to the machine. Instead, in 2015, Florian Weimer, a guy from Red Hat, demonstrated that it is possible to recover a private key also by remote. So this problem has some remote impacts. And he released the white paper. You can see there the link. But actually, he described the techniques without to release any tools and any exploits. And I will try to show you how this attack is possible, and at the end of this presentation, I will share with you some codes. So basically, this is what happened during TLS and shake. And normally, when the server certificate is exchanged, you can find the public key there. But if certain preconditions are met, I can demonstrate you that we can recover the private key without going beyond that line. So after just 4 TLS packets, if the preconditions are met, we can actually get the private key. So to recover the private key, we need 3 prerequisites. We need the presence of a RSA signature, which must be calculated using the RSA-CRT optimization. The signature must be applied on values that the attacker knows in clear text. And the generated signature, of course, must be faulty. So this means that the server in some way must miscalculate this signature. So first precondition is RSA signature. We need the RSA signature with RSA-CRT. Actually, the RSA operations are quite expensive, computationally speaking. So RSA-CRT was introduced, yes, to provide a less expensive way to do RSA operation, mainly decryption and signing. And this kind of algorithm is pervasive nowadays because it is implemented everywhere in every crypto library, we can say. So the precondition A is normally satisfied. So B, the attacker needs to know the value on which the signature is calculated. So we define X as the value that must be signed, and padding can in some way influence the final shape of the value that must be signed and make this value unpredictable, but likely from SSL 3.0 and from TLS 1.0 up to 1.2, basically the padding scheme used is deterministic. So it is predictable in some way. So we can say that the precondition B is always satisfied in our attack if we carefully target the right ciphersuites. And I will talk about this a little bit later. So the last prerequisite is the presence of a faulty signature. And this is the queen of the vulnerability, because without a faulty signature, we can't exploit this problem that I'm going to show you. So we identify this faulty signature with the letter Y. And basically, events that cause a server to miscalculate a signature are unpredictable in nature, but they are out there. And they are induced by the same vector that typically affect some other kind of technique. I don't know if you have heard about bit spotting attacks, but basically the presence of a faulty signature is possible if, I don't know, sometimes there is the overheating of the CPU, or there are RAM errors, or even exposure to the hardware to solar rays, for example. So what if the attack that we are going to place is successful? Actually, we can expose the private key of a server. And this means that the real server can be impersonated. And this basically means that you can place every man-in-the-middle attack that you want without alerting the regular clients. And when you place a man-in-the-middle attack, the difference from this to this is really important, of course. So when I mentioned the prerequisite B, I talked about, yes, that this attack to work needs to basically needs a signature, and this signature must be calculated on values that the attacker know. And of course, we need to negotiate the right signature for having back as an attacker a signature in the which has the characteristics that we want to exploit. So for example, if we choose as ciphersuite RSA with AES 256 CBC SHA. So basically, in this case, RSA is used as both has authentication and key exchange mechanism. AES is used as symmetric algorithm. CBC is the mode of operation. And SHA is basically the hashing algorithm. So in this case, if the private key is leaked, basically it means that we can compromise the current TLS session, but we can also compromise all the previously established TLS session and also all the TLS session established in the future. But unfortunately, the signature is exposed inside the certificate TLS packet, but the signature is created with the private key of the certification authority, and it is statically embedded inside the certificate, so it is not generated on the fly. So we can say that the precondition B is not satisfied if we try to use this kind of ciphersuite. And what about this other one? In this case, Diffie-Hellman is used as key exchange mechanism, and RSA is only used for authentication. And the rest is the same. So in this case, basically, the private and public key are generated on the fly. And the compromission of this session basically means that we can decrypt all the previous established session and all the future session because, you know, the private key and the public key are mainly, you know, generated differently each connection. And this feature is called Perfect Forward Secrecy. And actually, strangely enough, Perfect Forward Secrecy fits really perfectly to us because when we use this kind of ciphersuite, a signature is appended inside the server key exchange message, as you can see here. And most importantly, this signature is calculated starting from well-known value. And basically, they are the client random structure, which is taken from the client hello message, the server random structure, which is taken from the server hello message, and the server param structure, which is taken from the server key exchange message. All these messages basically are exchanged in clear text. So the attacker has access to these messages, of course. And remember, the padding scheme of TLS is deterministic. So basically, this kind of ciphersuite where Diffie-Hellman is used as key exchange mechanisms and RSA is used as authentication mechanism, basically are perfect for us. And this also means that we can exploit the technique that I'm going to show you, even if we are using the most modern elliptic curve algorithm. So this is basically what happened. We have here an attacker at the left side and the server right side. So the attacker sends a TLS client hello packet, trying to negotiate only perfect forward secrecy ciphersuite. And inside this packet, there is a random structure, which is a 32 bytes structure, which will be used to generate the signature. The server answers with a TLS server hello, and basically this contains as well a structure of 32 bytes, a random structure. At this point, the server answers with the certificate, and the certificate basically contains the public key, which is composed by two elements. The public key itself, so a modulus, which is called N, and the little exponent, which is called E, and it is basically always the same, 3 or 65,537. And finally, the server sends the TLS server key exchange message that embeds the server parameter structure, which is also used to calculate the signature. And finally, of course, the server in the same packet embeds the signature. So basically, after 4 packets, if the preconditions are met, we are able to decrypt a TLS session, so sorry, to derive a private key, and of course to decrypt a TLS session. So, of course, the queen of this vulnerability is the fact that we need to have a faulty signature. So we need to determine the presence of a faulty signature. But let's reason a little bit about that. So we know the padded scheme because it is, it is predictable, deterministic. And of course, we know the values on which the signature is calculated. So this means that as an attacker, we can calculate offline the expected signature. And because we have the public key of the server, we can also decrypt the signature that the server embeds inside the TLS server key exchange message. So basically, we can compare the signature that we have calculated offline and the signature that we get inside the TLS server key exchange message. And if there is a mismatch, this basically means that we have a faulty signature. So this is how it works on TLS minor than 1.2. So basically, we collect all the TLS message up to the server key exchange message. If TLS minor than 1.2 is used, basically, we calculate two hashes of the client random structure, the server random structure, and the server parameter structure. We calculate a MD5 hash and a SHA-1 hashes. We basically concatenate these two hashes, and actually it is the value which is signed by the server. So we have also the public key of the server, of course. So this means that we can decrypt the signature, and we will basically get the signature in clear text. We remove the padding from there, and actually we, compare the signature we have calculated offline with the signature that we have found inside the key exchange message. And actually, if there is a match, we are unlucky, so we can repeat the TLS and the shake. Instead, if there is a mismatch, so basically, we can try to recover the private key. And with TLS 1.2 is basically the same, except that TLS doesn't use a static MD5 and SHA-1 hash. Instead, TLS 1.2 uses a hashing algorithm, which is specified inside the TLS key server exchange message. So basically, it can be SHA-512, SHA-384. So it is negotiable in this sense. And this is the only difference. So if we have a faulty digital signature, we can, of course, try to recover the private key. How? To understand this, we need to understand also how RSA works, what is RSA-CRT, and after that, I will be able to give you a demo. So, how RSA works? So basically, this is the math behind RSA regarding encryption and decryption operations. So C is the ciphertext, so the encrypted message. M is the message that needs to be encrypted. N and D is the public key, basically, where is a little exponent, which is found inside the certificate. And N is a big number, which is actually composed by two prime numbers that we call P and Q. And D is actually the private key, which is calculated with that formula. And as you can see, to calculate the private key, we need three pieces of information. We need E, that you can find very easily inside the certificate, because it is a public information. And actually, you need P and Q, that basically multiplied together give you N. So if we are able to get P and Q, and actually because this is a public information, we can recover the the private key very easily. So RSA rule 1. So we have hand, which is the public key and which is a big prime number. If in some way we can get one of the prime factor composing the public key, it doesn't matter if P or Q, we actually can determine the other one. So just reasoning on small number, let's assume that we have a public key, which is 77, and for some reason we are able to leak one of the prime factor, for example, P. How we can get Q? It is very simple. We need just to divide hand by P, and we get Q. And if instead we have Q and we want to get P, we can just divide N by Q, and we get P. And of course, the multiplication of P by Q basically give us N, which is the public key. So the important aspect here is this. If we are able, basically, to get one prime factor of the two that compose a public key, we can basically derive the private key. So let's introduce RSA-CRT. RSA-CRT is basically an optimization that broke down the RSA calculation in two different pieces. So there is a precomputation of some values, which are this one. And instead, these other values are calculated dynamically. If during the M1 or M2 calculation there is a fault, actually the server will generate a miscalculated signature, and a prime factor, P or Q, can be revealed with that formula, which is the greater common divisor. Y is the, as I can show you, Y is the faulty miscalculated signature that we can take from the server key exchange message. E is the public exponent found inside the certificate. X is the original value before it's signed, and we know padding is deterministic, so the attacker can know that. And Han is actually the public key that we can find inside the certificate. So basically, this is the original Lenstra attack discovered back in 1996. So with this formula, we can get one of the prime factor. We can get P or Q. And when we know P or Q, we can basically derive the other prime number just by dividing hand by the prime factor. This gives us the possibility to derive a second factor. And we can use that formula basically to derive the private key. So this is the theory behind the attack. And after that, as I told you, we can recover the private key. And now, demo time. So I have basically created a couple of tools to exploit this technique. So this window here is the attacker window, and the window that you can find below is instead the server window. So server side, we have two OpenSSL versions. One is patched to generate faulty signature. And what I want to do now is, first of all, generate a new certificate. Sorry, a new private key, a new certificate, and a new public key. We are going to create a key which is really big for 4096 bits. I mean, really big for the standard of nowadays. OK. Here we have two certificate, new one.key, sorry, two files created. New one.key is basically the private key. New one.pem is basically the certificate. And we can analyze those in this way. There is the modulus, the public exponent, and the prime number, PRQ, etc., etc., etc. So now what I'm going to do is just to run this script. So basically, we are going to use the key and the certificate we have just generated to start up a TLS server on the port 4433. And basically, after 11 seconds, this process is stopped. And we start a new OpenSSL process, which basically run a version of OpenSSL that simulates the injection of a faulty signature. So what we will see is that for the first 11 seconds, we will have a fully working OpenSSL, a fully working TLS server. And after 11 seconds, we will have a process that instead injects a faulty signature. And to exploit this problem on the attacker side, we are going to use this tool, which is called High Voltage. I gave the name to this tool when I was listening the famous AC/DC song. I guess that you know who are AC/DC. So basically, these tools take the IP address of the server, it takes the port, and yes, we can decide if use TLS 1.2 or not. So I'm going to launch the server part, and I'm going to launch the attacker part as well. So the attacker starts to establish connection over and over and over. And at some point, when a faulty signature is generated, is able to catch this situation, and the tool is able to recover the private key. So the proof is this. OK. OK. As you can see here, you have a match. So this means that on server side, oops, sorry, and on client side, you have the same value. So the attack was basically successful. Yes, you can see here, for example, this part and this part as well. So as an attacker, we were able to recover the private key. But you can do this attack in two ways, basically. You can establish handshakes over and over and over, or you can just sniff the traffic. And at some point offline, you can determine if inside the traffic there is a faulty signature, and you can derive the private key. For example, for doing that, I created the second tool, which is called Picciola. Don't ask me what it means. So basically, I have this directory where there are 4 dumps, 4 traffic dumps on different port, different protocol, etc. I'm going to copy all of these inside the stream directory. And inside the stream directory, probably this was a refuse. OK. Let's clean it up. OK. So what I'm going to do is use the TCP flow tools that basically analyze each of these files, which has been taken with TCP dump. And basically, what we get is a stream. So each connection, is characterized by the client data that are sent to the server and the server data that are sent to the client. So basically, TCP flow splits this stream and extract these streams and put this stream singularly inside different files. So we can analyze this file easily in this case. So what I'm going to do now, I'm going to use this script that actually called the binary called Picciola. And I'm going to give as an argument the directory where all the streams have been copied. So basically, Picciola will analyze all of these files one by one, trying to determine if there is a faulty signature and trying to derive the private key. There's a bunch of verbose message for that. So and actually, when the analysis is finished, we can see different directories. So we have the incomplete directory. In this directory, you can find all the streams that have only one side of the communication. So for example, only the communication from client to server, but not the stream from server to client. So the tools put this stream inside the incomplete directory. And inside the not TLS directory, you can find all the streams that have not been identified as TLS connection. So have been discharged. And inside the result, actually, you can find two directories. So this means that the tools was able to recover two different keys. And inside each of these directories, you can find the two files representing the communication from the client to the server, from the server to the client, and of course, the certificate, the private key, and the public key that it was able to derive. I'm going to finish. OK, the bottom line is that if you have a piece of software linked to a vulnerable crypto library using RSA-CRT, and if the crypto library doesn't verify the correctness of the signature, and if there is an environmental problem that causes the miscalculation of the signature, of course, you are in trouble because your private key can be derived. And the fix is quite simple. Basically, you have to install a patch because few crypto library, a few crypto library gives you the possibility to disable RSA-CRT optimization, but this is not suggestible because, for performance, it is not convenient to disable RSA-CRT. But a lot of vendors basically issue a patch for their crypto libraries that basically do a double check of the RSA signature without RSA-CRT optimization. And this is the list of the crypto libraries identified as affected so far. You have PolarSSL, you have Java, OpenSSL, Go, CryptoLib, WolfSSL, OpenSwan, I will talk about that a little bit in the last slide. These are the hardware vendors affected so far. And the device types mainly affected are embedded device, just like firewall, routers, SSL accelerator, VPN concentrator, stuff like that. And yes, the problem here is that you are vulnerable if you are using a crypto library that is linked to, yes, a vulnerable, if you use a piece of software that is linked to a crypto library vulnerable that are using RSA-CRT. But this problem is not only related to TLS, because Perfect Forward Secrecy and RSA are used also in EK Internet Exchange, Key Exchange, protocol, which is part of the IPsec stack in SSH, DNSSEC, etc. So probably the TLS service are not the only one affected by this problem. Before to conclude, let me give you a special thanks to my colleague Frank Bosman that provided me the nice picture. And of course, Florian Weimer, which must be credited for the discovery of this technique, for the remote impact of this technique. And if you want to understand under the hood how the tools that I created works, High Voltage and Picciola, you can download the tools from that link. The tools are not still available, but I will publish them hopefully in the weekend, but maximum before the end of the next weekend, they will be online. So I want to thank you for joining me today, and if you have questions, I'm here to answer.